Hello everyone, and welcome to the Radar System Design and Analysis with MATLAB webinar. My name is Vincent Pellissier. I'm a development manager in the Signal Processing and Communication department here at MathWorks. Today, I'd like to show you MATLAB tools that help you design and analyze radar systems. First, we'll review the challenges of modeling radar systems. Then I'll show you through 3 examples how these challenges can be addressed. First, we'll model a phased array antenna with a complex geometry. Then we'll see a beamformer example where an array is mounted on a vehicle and needs to track a moving target. And for the third example, we'll model a complete end-to-end radar system. The application focus for today's webinar is surface, that is ground-based or sea-based, and airborne radar systems, but also automotive radar systems. I'll highlight a few other key features that didn't fit in the examples, and we'll wrap up this presentation with a Q&A session. At a high level, a radar model is comprised of the following components: a waveform generator, a transmitter, transmit and receive arrays, an environment including propagation, target, and interference models, a receiver front end, and array signal processing algorithms such as beamformers and direction of arrival estimators. Radar engineers face several challenges when modeling such systems. First, in the spatial domain, they need to represent the various array geometries, linear and planar arrays, but also arrays that conform to a particular surface, such as the wing of an airplane. They also need to represent different transmitter, target, receiver configurations, whether the transmitter and receiver are collocated, as in the monostatic case, or not, as in the multistatic case. Next, in the time domain, they need to represent platform motions and target vehicle dynamics and their associated signal effects, from Doppler shift to amplitude and phase variation. And finally, in the spectral domain, they need to represent desired waveforms, as well as noise and interference sources such as jammers and clutter. Next, I'd like to give you a quick overview of tools available in MATLAB that can help you address these challenges. The most relevant tools are packaged in the Phased Array System Toolbox. This is a newer product. We just shipped the 4th release in our 2012B. It is a system toolbox that provides algorithms, models, and visualization tools for designing, simulating, and analyzing systems with distributed sensors, including phased array radar systems, of course. It offers radar engineers a consistent methodology to reduce the time needed to design, analyze, and implement radar systems by providing models for transmit arrays, receive arrays, waveforms, targets, clutter, etc. And it also enables engineers to build scalable, reusable system models and signal processing algorithms. Now it's time to look at a few concrete examples. Let's start with an essential part of the radar, the phased array antenna. In this first example, I'll show you how to model a pyramidal conformal antenna array made of 4 panels. This low-profile antenna could be mounted on the roof of a vehicle, as illustrated on this slide. We'll visualize the array geometry and the radiation pattern of the antenna. Now let's run that simulation. On the left plot, we see the response pattern of the array with isotropic antennas and a phase slope of 4 to 5 degrees. On the middle plot, the phase slope is still 4 to 5 degrees, but each antenna element has a cosine pattern instead of an isotropic pattern. On the right plot, we see the response pattern of the array with cosine pattern antenna, but a phase slope of 75 degrees. Comparing this last plot to the previous two, notice how the array span has changed. The array is approximately 4 cm taller and 7 cm shorter in X and Y dimensions. We can further explore the 3D geometry by changing the viewing angle. From the side, we see that the array with the steeper slope on the right has the narrowest beam. This steeper configuration is probably better to track targets on the ground, while the 45-degree slope will give better performance in a satellite tracking application. From the top, we verify that the array with the cosine pattern antennas are significantly more selective. That means have sharper beams and lower side lobe than the array on the left with the isotropic antennas. Now, let's take a look at the code behind this simulation. This example is divided in 3 sections that corresponds to the 3 plots we've just seen. First, we define a single panel or subarray as a 4x4 UArray and specify the frequency range in which the antenna operates. Here, the array operates in S-band from 2 to 4 GHz. By default, arrays are made of isotropic antennas. Here we choose to turn the back baffle property true. We then replicate the subarray 4 times to conform to a pyramidal shape. We first set the slope of each face to 45 degrees. In the second section, we replace the isotropic antenna with a cosine pattern. In the third section, we change the slope of each face from 45 to 75 degrees. In each of these 3 steps, we visualize the array geometry and the array response. Let's look at this code as well. This code is a little bit fancy because of the plot-in-plot capability, but notice that each visualization can be achieved by a single command. The view array to plot the array geometry, and the plot response to visualize the 3D radiation pattern. Now let's go back to the presentation. What did we see? We just saw that a complex array geometry can be modeled with only a few lines of MATLAB code. And this allows us to leverage MATLAB interactive 3D visualization tools to quickly get insight in the array response. What else does the Toolbox offer in that area that we didn't see? We could have modeled other array shapes, such as circular or hexagonal arrays. We could have modeled array tapers, or thinning, or dead elements. We could also have modeled overlapped and non-contiguous subarrays. Now let's do something a little more complicated. We're going to reuse the array we've just designed and mount it on a vehicle that needs to track a moving target. We need to model several more pieces of the system now. The platform motion, radiator collector, and a beamformer. Let's run this example. On the first row, we see the antenna and target trajectories in the global coordinate system and in the local coordinate system, that is from the antenna perspective. In that plot, notice how the target appears larger as it moves towards the antenna and smaller as it moves away. On the lower right plot, the active faces of the array are highlighted. Notice how 1 or 2 faces are active at any given time depending on the position of the target, and how this is reflected on the bottom left, where the array responds as a narrower beam when 2 faces are active. All right. Now, let's take a look at the code behind this simulation. The first thing to notice is that the code is divided in 2 sections, a model section and a simulate section. In the model section, this is where all components are created. In the simulate section, this is where the streaming simulation loop and the communication between the different components is defined. Taking a closer look at the initialization section, we see that we split each subarray and model them as 4 independent arrays. For each of these arrays, we define a collector, a conventional phase shift beamformer, and an array response component. The 4 arrays share the same platform. The initial position and velocity of the target are also specified. The simulation loop is only 15 lines of code. For each step, we update the antenna and target position, we calculate the relative antenna target angle, and we collect the signal from the target direction. We then add some receiver noise and beamform in the target direction. Finally, we combine the output of the active arrays and visualize the trajectories and array response. What did we see? We just saw that the special effects of a simple radar system can be easily modeled and simulated. We also saw another way of computing and plotting the array response that is better suited for streaming and live visual updates. Different interfaces are available to do different things easily and efficiently. What else does the Toolbox offer in this area that we didn't see? We use the conventional beamformer here, but we could have used an adaptive beamformer such as KPON or MVDR or even LCMV instead. We could also have added a jammer and monitored the SNR at the output of the beamformer. Finally, we assumed a narrowband antenna, but we could have used a wideband antenna along with a time delay or subband beamformer instead. Let's move to our third example. In the previous example, several components such as the waveform, transmitter, and target models were omitted. This time, let's look at a complete end-to-end radar system. In this example, I'll show you how to model and simulate a ground-based monostatic pulse radar. Here again, we'll reuse the same antenna array in the interest of time, but we'll also define all the major components of the system, from the waveform to the transmitter to the targets and propagation channels to the receiver. We'll visualize signals at different points of the system, and we'll estimate the range and speed of 3 targets. The radar we model has the following high-level parameters: an 8 kilometer maximum range, a 50-meter range resolution, a probability of detection of 90%, and a false alarm rate of 1 per million. So now let's run the simulation. On the first row, we see the transmitted and collected signals. Notice the small magnitude of collected signals reflecting all propagation losses. On the second row, we have a range Doppler map and an estimated range plot. The range Doppler map gives us a first idea of the theater. We see 3 distinct targets at range between 2 and 3 kilometers, around 5 kilometers, and around 6 kilometers. The closer and farther away targets appear to move away from the antenna at a speed of respectively 100 meters per second and 320 meters per second, while the middle target seems to be moving towards the array at a speed of 400 meters per second. On the lower left plot, we see that the 3 target echoes are clearly above the detection threshold. We can even read finer estimate of the ranges because further signal processing, including pulse integration, has been applied to the signal. Finally, we see that the target have started to move away from their initial positions, visualized as the red vertical dotted lines, but not by much. This is because we've only simulated about 90 milliseconds so far of this scenario. If we let the simulation run longer, the effect will be more dramatic. Now, let's take a look at the code behind this simulation. Here again, the first thing to notice is that the code is divided in two sections. The model section, where all the components are created and parameterized, and the simulation section that contains the simulation loop and the communication between different components. In the model section, we start with the high-level parameters of the radar, such as the maximum range, range resolution, probability of detection, and false alarm. The pyramidal antenna array is mounted on a vehicle moving at 67 miles per hour or 30 meters per second. Then we define the transmitter. Let's look at it in more detail. The transmitted waveform is a chirp whose PRF is derived from the maximum range and sweep bandwidth is derived from the range resolution. The transmitter peak power is calculated with the radar equation and Schneidman equation. Finally, the antenna platform that will control the motion and the radiator models are also defined here. Next, let's look at the theater. 3 targets are modeled as fluctuating point targets. They are defined as swelling 2 models of their mean RCS. The mean RCS are 1.2, 1.1, and 1.05 square meters respectively. The targets are set in motion at various speeds, from 220 miles per hour, or 100 meters per second, to 90 miles per hour, or 400 meters per second. Each propagation channel from the array to the target is modeled as free space. Because the system is monostatic, we turn the two-way propagation mode on to gain a little bit of simulation efficiency. Okay, so we've seen the transmitter, the theater. The last part is to look at the receiver. We assume far-field signals at the receiver array. Plane waves are collected and noise is added through the receiver preamp. The signal processing chain is made of 4 components: range Doppler response estimator, a match filter component, a time-varying gain that needs to be adjusted for the maximum range of the radar, and a Neiman-Pearson detection threshold. So that's it for the model. Now, how do we run the simulation? Well, in this example, we've run 2,000 pulses. We transmit the pulse, update the antenna position, then for each target, we update the target position, calculate the relative angle between the antenna and the target, and radiate a signal towards the target. We then propagate the signal to the target, reflect off the target, and propagate back. All signals impinging on the array are collected, and the output of the subarrays are combined. The signals go through the receiver preamp and time-varying gain control. And then the range Doppler map is produced, and further processing, including pulse integration, is applied to refine range estimation. Now let's return to the presentation. What did we see? We just saw that a complete end-to-end radar system can be easily modeled and simulated. This last example hopefully illustrates a scalable framework for radar engineers to easily reuse and share their radar system models. What else does the Toolbox offer that we didn't see? We saw a few analysis tools, such as one version of the radar equation to calculate the transmitter peak power. The toolbox also offers two more versions to calculate the maximum unambiguous range or the SNR of the system. We could also have plotted rock curves, or we could have defined a surface clutter and design a moving target indicator to mitigate clutter effects. Finally, we could also have estimated the angles of the target and produce a range angle map or plant position indicator. This concludes the demo part of this presentation. I'll highlight a few other key features that didn't fit into the examples, and we'll move on to the Q&A session. Radar engineers work with common antenna array geometries, such as the uniform linear array and the uniform rectangular array, but also arbitrary geometries as we've seen today. Here are a few examples of linear, planar, and conformal arrays and subarrays generated with the product. Another important characteristic of an antenna array is the radiation pattern of the individual sensors. The toolbox lets you specify your own custom element response using either analytic expressions or measured data. I've shown you a couple 2D and 3D visualizations of the array response, but you may also be interested in looking at the array response at multiple frequencies if you work with wideband antennas, or you may prefer to look at this data in UV space. We went quickly over the design of the waveform in the last example, but here again, whether you work with pulse or continuous waveforms, frequency modulated or phase coded, with or without staggered PRF, you'll find tools to model and analyze your waveform, such as different ambiguity function visualizations and time frequency plots. On the signal processing side, we've seen one basic beamformer algorithm today, but the toolbox offers both conventional and adaptive beamformers for narrowband and wideband applications. The toolbox also supports directional arrival estimation, including monopulse, beam scan, and high-resolution techniques such as esprit and root music. We've seen that we can easily generate a range Doppler or range speed map, and here are a couple more examples of range angle maps generated with the toolbox. Finally, you also find models for jammers and surface clutter, along with several STAP algorithms. We don't have time to cover everything in detail today, but the toolbox has a collection of tutorial and application examples. An important thing to notice is that everything in the toolbox is written in MATLAB, which means you have access to all the code. This makes featured examples in particular an excellent place to start developing your own models. It's now time to summarize and wrap up. So in summary, the phased array system toolbox lets you rapidly model and simulate phased array systems in the familiar MATLAB environment. You can interactively develop systems with specific models and tools for phased array systems. You can also use a rich set of algorithms for temporal, spectral, and spatial signal processing. As for the next steps, I invite you to visit the Phased Array System Toolbox site on mathworks.com, where you'll find more information, including examples, complete documentation and product description, and recorded webinars.